Another application concerns compound interest and present discounted values. Here I'll just recall what we have done earlier. So let us suppose if I have f of t, I know that it denotes the stock of any quantity at time t, and in this case f prime t by f of t, this denotes the relative rate of increase of the stock at time t, and there are cases wherein this is a constant r, that is the relative rate of increase is a constant r, and the functions having a constant relative rate of increase, those are functions of this type a e raised to the power rt. So we have done this point that if we have f prime t is equal to r f t, this is if and only if f of t is of this type a e raised to the power rt. So this is something we have already covered. Now this particular fact, and in fact even this, both of these have very important applications in economics also, and a very important application in that sense concerns compound interest and present discounted values. So what we now do is that if we think of a deposit of k dollars, let's say this deposit earns interest at this rate, that is p% per year. After t years, what will this deposit get to? As in after t years, the deposit of k dollars will actually increase to k multiplied by 1 plus r raised to the power t, wherein r is equal to p by 100. So this k dollars would have increased to k multiplied by 1 plus r raised to the power t after t years, wherein this r is equal to p by 100. Keeping this in mind that the deposit is earning interest at the rate of p% per year. So basically here we see that in this case, if I say after t years, this will be the, or in other words, I can say that after t years, k dollars would have increased to this amount. After 1 year, it would have increased to this amount. After 2 years, it would have increased to this amount. What I mean to say here is that each year, the principal increases by this factor 1 plus r. So each year, that principal of k dollars, it actually increases by this factor, which is 1 plus r. So in this case, if I talk about the fact that after t years, the deposit of k dollars earning an interest at the rate of p% per year would increase to this. This actually reflects the fact that each year we are adding interest to the principal, as in after the end of each year we are adding interest to the principal. In this case, we are adding interest to the principal after each year. Let us suppose we are adding interest to the principal after each 6 months, but at the interest of p by 2%. So now the point that I'm trying to make here is that I'm adding interest to the principal after 6 months rather than a year, and the interest rate is, instead of p%, the interest rate is p by 2%. That means after half year or after 6 months, my principal would have increased to k plus k multiplied by p by 2 by 100. Because what I'm trying to say here is that the interest rate is now P by 2%, and I am adding interest at the end of 6 months. So after 6 months, my principal, which is K dollars, will increase to this expression, will increase to this amount. And this can then be written as K 1 plus P by 200, or in other words, I can write it as K 1 plus R by 2. Again, R is equal to P by 100. So now we see this is what the principal would increase to after 6 months. After another 6 months, principal would increase to this. After another 6 months, the principal would increase to this. So in fact, after 1 year, the principal would increase to this. After 1 year. And this would be after 1 year 6 months. So if after 1 year the principal would have increased to this amount, keeping in mind the fact that we are now adding interest after every 6 months, and the interest rate is P by 2%. Now after T years, the deposit of K dollars would actually increase. So now after 1 year, this is the case. So after T years, the deposit would increase to K 1 plus R by 2 raised to the power 2t. So after T years, what is this amount? This is, I can now write after T years, K would increase to this, when interest is added after each half year. After each half year at an interest rate of P by 2. And the point to note here is that when we talk about, so this is a biannual interest payment, wherein interest is paid when I say biannual, that means 2 times in 1 year. So it's a biannual interest payment at the rate of P by 2%. What I'm now proposing is that this biannual interest payment at the rate P by 2%, biannual interest payment at the rate P by 2%, this will be better, or this is better for the lender. When I say better, I'm comparing it with the annual interest payment at the rate P%. Is better for the lender. Now when I talk about lender, that means I'm concerned about more and more interest. So the point that we are going to make here is that this biannual interest payment is going to be more than the annual interest payment. It is better for the lender than annual interest payment at the rate P%. And that means, so biannual interest payment is actually will actually lead us to k 1 plus r by 2 raised to the power 2, this after 1 year. And in this case, the point that I'm trying to make is that this is greater than k 1 plus r. Now that means 1 plus r by 2 squared is greater than 1 plus r. Let's try to see if this is indeed the case or not. So let's take up 1 plus r by 2 squared. This is in fact equal to 1 plus r squared by 4 plus 2 1 r by 2, and this actually gives us 1 plus r squared by 4, which clearly is greater than 1 plus r. And that means we have now established that the biannual interest payment at the rate P by 2%, it is better for the lender than annual interest payment at the rate P%. Earlier I talked about interest being added after each year. Then I talked about interest being added after each 6 months. Now let's say we suppose that interest is added n times in 1 year, and when I say n times, those times are distributed evenly over the year, and the interest rate is, so earlier when we talked about interest being added after each 1 year, interest rate was P%. Then we talked about interest being added after each half year, then the interest rate was P by 2%. Now the interest rate would be P by n%, because now what we are doing is we are adding the interest n times over that year, and that means n times distributed evenly over 1 year. So that's what I take up. Interest is added at the rate P by n%, and the interest is added at this rate, and we have to understand that it is added to the principal n times distributed evenly over the year. What does that mean? That means after each year, that means after 1 year, the principal would be, so if the deposit is K dollars, the deposit after 1 year would move to 1 plus r by n raised to the power n. Earlier it was this 1 plus r by 2 raised to the power 2. Now it is 1 plus r by n raised to the power n. So this is what the deposit would get to after 1 year when we add the interest rate, when we add the interest n times distributed evenly over the year. We have to keep this in mind that r is equal to P by 100, and that means the interest rate is P by n%. So this is what the deposit would get to after 1 year. After t years, the principal would increase to this 1 plus r by n raised to the power nt. This would be the amount after t years. Now the point to note here is that the greater this n is, the more profitable is that investment to the lender. The greater this n is, the more and more interest payment the lender receives. And that means the greater the n is, the more profitable the investment is for the lender. The greater is n, the more profitable is the investment for the lender. Basically, when we have one, and we have actually proved this from n being 1 to n being 2. So first we saw that if you have, so we have actually seen that the biannual interest payment is better for the lender than an annual interest payment. Biannual interest payment at the rate P by 2% is better for the lender than the annual interest payment at the rate P%. That just means that when you increase this n, the more profitable is the investment for the lender. So the greater is n, the more profitable is the investment for the lender. But when we talk about n being greater and greater, we have to understand that surely when I talk about n, that means I'm adding interest. So let's say earlier I was adding interest after 1 year, then I was adding interest after 6 months, then let's say I'm adding interest after 3 months, and then let's say I'm adding interest after 1 month, then I'm adding interest after each week, or then I'm adding interest daily, and then I'm adding interest in an hour, as in hourly, and then I'm adding interest per minute, then per second, then per millisecond, and so on and so forth. So what I'm saying is that as I increase this n, but there is a limit. To what extent can I increase this n? So the point to note is that there is a limit to how frequently I can add interest to my saving account, or how frequently I can add interest to my principal amount. So that means in this case, if I talk about this expression k 1 plus r by n raised to the power nt, what is this amount? This is the amount to which the principal will increase, the principal of k dollars will increase when we are adding interest n times distributed evenly over the year, and this is what the amount will be after t years. When each year we are adding interest n times distributed evenly over the year. The point to note is that this n has a limit, as in it's not that n has a limit, there is a limit to how frequently I can add interest to my savings account. So for that, what I have to understand is what this expression will tend to as n tends to infinity. So when I say n tends to infinity, that means we can suppose that interest is being added for a fraction of a second, wherein that fraction gets smaller and smaller and smaller. And if that is the case, that means we are making this n, we are actually approaching n towards infinity. We are making n approach towards infinity. So we actually have to see what happens to this expression as this n tends to infinity. Then we will see what happens. Then when we see what happens to this expression, that will actually give us a perspective on the fact that there is a limit to how frequently interest can be added to the savings account. And when we so the point to note is, I think I don't want anyone to get confused here. In general, or in practice, or in reality, there is a limit to how frequently interest can be added to savings account. The point to note is that this n, in practice, this n cannot tend to infinity. It's not that you have interest being added to the principal amount after each second, or after each millisecond, or after each nanosecond. That's not the case in reality. But we have to understand what will happen to this expression as n tends to infinity. So if n tends to infinity, that means interest is being added. Think of it as a millisecond or a nanosecond, and in fact even less and less than that nanosecond. So that is something we would like to know, as in what happens to our expression here as n tends to infinity, or what happens to that k dollars, what happens to our deposit when interest is compounded. So now the compounding is continuously. So earlier we were talking about annual compounding, then half yearly compounding, then maybe quarterly compounding, then monthly compounding, then daily compounding, then hourly compounding, then when I say hourly compounding, then compounding per minute, then per second, then per millisecond. So what happens as we decrease that interval, and we just compress that interval closer and closer to zero, not obviously equal to zero, but tending towards zero. So in that sense, the compounding is going to happen continuously. In that sense, n would actually tend to infinity. So we would just like to know what happens to this expression as that annual frequency, as that frequency n tends to infinity. In practice, that's not the case. In practice, there is surely a limit to how frequently interest can be added to the savings account. So in practice, n is definitely not infinity. N is definitely not tending towards infinity. But we would like to know what this expression would tend to as n tends to infinity. For that, what we do is we put r by n equal to 1 by m. And that gives us n is equal to mr. And now we can see this expression. What happens to this expression? k 1 plus r by n raised to the power n t. So I can write that as k. When I write 1 r by n, so I know r by n is equal to 1 plus, so r by n is equal to 1 by m, so I write that. And n is equal to mr, so I write mr t. This can then be written as k 1 plus 1 by m. In fact, I can write this raised to the power rt. And I would now like to know what happens to this expression as n tends to infinity. But I know from here that I know r is greater than 0, r is fixed. And as n tends to infinity, m, I know from this expression, I know that m is equal to n by r. As n tends to infinity, with r being fixed, m also tends to infinity. So as n tends to infinity, I know r is fixed, it's a fixed positive. M also tends to infinity. So if m also tends to infinity, I can then see what happens to this expression as m tends to infinity. And if I want to know this, that means I want to know limit m tending to infinity k 1 plus 1 by m rt raised to the power rt. I know that this expression tends to e as m tends to infinity. We know that. That means this is equal to k e raised to the power rt. So what I mean to say here is that this expression tends to k e raised to the power rt as n tends to infinity. So if we let n approach infinity, that means we think of the accumulation of interest happening more and more frequently. In that case, in the limit, we are actually thinking of continuous compounding. Compounding is occurring continuously. It's not occurring daily, it's not occurring hourly, it's occurring continuously. It's occurring in a manner that we can't even measure. So the compounding is occurring continuously. So this is what we call continuous compounding. So when I talk about continuous compounding, that just means n is approaching infinity. So if you have continuous compounding, given the fact that n approaches infinity, now if you have k dollars, that's the initial amount, it will now increase to, this will increase to this expression. It will increase to and here we often refer to this r as the rate of interest. Now if I differentiate this expression, I see that I have this. So if I have kt is equal to ke raised to the power rt, what is this expression? This is the amount to which the initial amount k would increase to if interest is added continuously, if you have continuous compounding of interest. And if I want to differentiate this with respect to t, I have this is equal to ke raised to the power rt, and then I should write r. So this is equal to r kt, and basically now I have k prime t by kt equal to r. This is something to note. That when our compounding is continuous, when we have continuous compounding of interest at the rate r, then we see that our principal amount is in fact increasing at a constant relative rate. So in fact there is a constant relative rate of increase of the principal at the rate r. We have k prime t by k of t being equal to the constant r. This is when compounding is done continuously, when we have continuous compounding. So this is a very important point to take note of, that with continuous compounding of interest, with continuous compounding of interest at rate r, the principal increases at the constant relative rate r. And you can see that the continuous compounding of interest is at rate r, wherein please keep this in mind that r is nothing but p by 100, and that means the principal is actually increasing at the constant relative rate r. That means you have k prime t by k of t being equal to r. Now if I have this, from this, if I think of k of 1, this will be k e raised to the power r. That means my principal, which is k, it has increased by this factor e raised to the power r just in the first year. So in the first year, my principal has increased by this factor. And if I just think of kt plus 1, that actually gives us k e r t plus 1. So this is equal to k e r t. Then you have e r. So that's nothing but k of t e r. That means when you have continuous compounding of interest, each year my principal is going to increase by the fixed factor e raised to the power r. That's a very important point to take note of. That when we have continuous compounding of interest, we clearly have continuous compounding of interest here. And if that is the case, the principal is going to increase each year by that fixed factor e raised to the power r. So this is something we can write with continuous compounding of interest. The principal increases each year by the fixed factor e raised to the power r, this one.